folks, or good morning if you are on the West Coast or Chicago or wherever. I'm very glad to talk to you on this, probably the most important current topic. I look outside and see the beautiful world, the river. I see the river, Hudson River from here, the trees. And so the world is beautiful. And to see that, enjoy it, we have to have health. Health is the most important issue for all of us. And as you know, the virus is threatening it. And understand that it will continue to threaten in another form or not in the future. And we have been, the most important thing is to mitigate spreading. That's the only way to mitigate the spreading or control the spreading. And we have been working on use of foams and bubbles to mitigate the spreading of actually Ebola virus at that time. And that's what I would like to talk about today. And by the way, at the bottom of it, you see my email, and you see the Indian Namaste, and at the bottom right, you see the Asian bow, which is much safer than coughing into elbows because elbows are often dirty. So Partha Patra is the co-worker, and Mark also has been helping me, and Ray and Nagaraj. So second slide, please.
You're on slide 2 now.
Okay, slide 2. So what you see on slide 2 is applications of surfactants, polymers, and proteins in many areas, for environmental, personal, and healthcare. I won't talk about all of them, but you see the left hand top, you see bubbles and droplets lifting minerals, and I'll come back to that again when I go to space applications. And the next to that, on the right hand side, you see how one can increase the nitrogen utilization when you use fertilizer. And next to that is oils, enhanced oil recovery, how you increase the oil recovery from 10% to 30 or 80% using surfactants. And of course, there are problems of oil spill that is shown on the right hand side, which you can also control using surfactants and polymers. On the bottom leftmost is the beautiful illustration of hydrophobicity. You see a leaf floating there, but not being wetted, and so will the flower also will not be wetted. And that particular phenomenon is very important in this mitigation phenomena. And next to that is the fracking, and next to that is our current topic, and that's the coronavirus. And next slide shows.
You're on the next slide now.
Yeah. Next slide shows the. I'm going to. I'm seeing your slide because.
We're on disinfectant products, so.
Yeah, I'm trying to see that on my slide, and I don't see that. So let me go back to. Oh, I am seeing actually your slide, Mark. So the bleach solution is used for disinfection. There are several problems. One is that the bleach fumes cause lung burn if inhaled too much, and then combined with ammonia and so on, which is in many products such as Windex, they can also create chloramine gases, highly irritating. And bleach, an acid like vinegar, can create deadly chlorine gas. So there are a lot of problems in using bleach solution. The other problem I want to illustrate here using my cup here. Oh, you cannot see my screen. Can you see my screen? Oh, let me see. Yeah, you can see my screen, right?
No, we can't see your image.
Oh, say okay. I'm holding it, so you don't see me?
No, we're not seeing a video.
Okay, not video. My holding. Do you see my face?
Do not.
My beautiful face.
Um,
What is-
your camera is off, so
Oh, I didn't do that. Okay, view options. Let me see. Okay, it doesn't matter. What I have was going to show you a demonstration of if I spray water on my plastic cup here, it will just drip. But I have in my hand, which you cannot see, the shaving cream, which is just foam. And if I spray that on my cup here, it will stay there. It will slowly come down, it will stay there. So in other words, when you say bleach solution, it doesn't stick, whereas something like a foam will stick. So when you spray bleach solution to decontaminate protective clothing or trucks and so on, it doesn't do much because it doesn't stay there. Whereas if you use foam, it can stay there, and using the right composition, you can control how long the foam will stay. For example, you need about half an hour to kill a virus. So that's the whole idea. Next slide. So this slide shows the problem of using the current disinfectants. They irritate skin, can lead to rashes, and exposure to some other substituents can affect sperm quality, reducing fertility, and also resulting in birth defects. Can you imagine it? So widespread use of substituents can also create superbugs that are resistant to antibiotics. Next slide. And the current state of decontamination is what is shown on this slide. So on the top left, you see the protective clothing. If you spray bleach solution, it will just drip out. That's the problem. And another primitive method is shown on the extreme right. They use chlorine dioxide gas in zip bags so that when you unload corpses, dead bodies from a truck, you can immediately decontaminate. That's the kind of crude methods that are used. Obviously, this is not very effective. And if you apply the hazmat on protective clothing, as I said, it drips and you won't get complete decontamination. The other problem is that when you use bleach solution, there's a lot of water in it, toxic water, and that will seepage through the ground and contaminate the areas. Now, one problem, there's a lot of talk about swabs. Swabs are used, but swabs are like these brushes, which has, depending upon the hydrophobic and hydrophilic, it may not be very effective. So this particular phenomenon is to be kept in mind when you design a swab. Next slide. So this shows beautiful picture of foams. The dry foam on the left-hand side. The dry foam means which is very little liquid between the bubbles, and the wet foam has a lot of liquid. So dry foams, if you use dry foams, the volume occupied by the foam material is small. So when it dries, when the foam breaks, there's not much effluent to contaminate the sewers and so on. So that is the idea, to use dry foam. Next slide. Here I show some of the applications of foams. The foam, you can see this is semi-dry foam. And next slide shows the foam on the bottom of shoe. That's a solid foam. The next one, this one you'd like. Wake up. You can have a sip of it if you have some beer near you. And you see this is the foam, and that is that an application that all of you will know, right? Okay, next one. And the foam that is used in cushions as shown here. And the next one shows how foams are also used to put out fire when an airplane or something catches fire. And the next one shows how you spread the foam on a tarmac so that when a plane has to land, it doesn't crash. It will crash, but it won't kill. One plane crash, there was no injury at all because foam was acting like a nice bed to take the impact of the plane crash. The next one. And this is a very summary slide of the foam spray benefits. Unfortunately, I cannot use, but if you use the tracer on application, the application of the foam, with the foam you can reach difficult to reach places such as rooftops. If you have to clean, Mark asked me yesterday, why rooftop? Well, cars and also hospitals, and ceilings and cracks and pores. Cracks and pores are where the viruses can hide. And if you just rinse for 20 seconds, they may not get killed. Whereas if we use silicone surfactants, is a super spreader, along with the surfactant, then it can penetrate. My first student, Kulkarni, has a company in India which makes the silicones. So with that, you can penetrate the ceilings, cracks, which I'll show in one of the next slides. And also you can get better adherence for, let's say, like 30 minutes that's required to kill viruses. And also when you use a foam, there is minimal splashback. You see the Partha and his assistant spraying foam on a screen on the Columbia, actually in front of the garage at Columbia at 7 o'clock in the morning. I'm not a morning person, but he went there to test it, and you can see that it sprays there. And you can also test the application of it using some sensors. Before foaming, the sensor is white, but after foaming, the bleach. Oh, okay. And you get better adherence for better time and minimal splashback. You can also reach larger distances, and you can use automated deployment options, which I'll show you in one of the next slides. And one of our main efforts under a current NSF grant we got is to substitute greener biosurfactants instead of bleach. You don't want to pour bleach on your face and hand, even though Washington, D.C., some people have been recommending drinking bleach. I wouldn't do that, and I wouldn't apply that on your face either. So our approach is to use greener biosurfactants, which will do the same thing, hopefully, as bleach. And that's what Partha, I think he's listening, he's working on. Yeah, also you can formulate this on site. You get concentrated material and you can make the formulation right on the site and apply it on sprayers, and you can decontaminate airports, planes, trucks, etc. And there'll be no fumes or mist. Whereas if you use bleach, you can smell it and create problems. And so next slide. So that shows at the bottom the acoustic ceilings, which has cracks, and also at the bottom you see carpets under which the virus can hide. Remember that microbes and viruses are much smarter than all of us put together. So once we are very careful, they can beat us. And we can control the texture of foam by using the type of surfactant and the dosage. You can get nano-textured foam which can penetrate into cracks and edges if you use silicones. And you can deploy it using the sprayers shown on the bottom right, all the way from the small one to the big ones. You can use that to get to anywhere. And you can also control the target surface attachment, with no splashing. That's the best advantage of foam. Next slide. Yeah, that shows. Oh no, stay there. Stay there. Okay, stay on this slide. Okay, actually here you see some beautiful applications of surface colloid chemistry. On the top left, you see the thinning of soap bubble. If you have played with soap bubbles when you're a kid, if you didn't, there is something wrong with you. You need to try soap bubbles. You see these colors because the thickness of the film changes, and as the thickness changes, you see the color. And at the bottom, as long as you're on the, go back one slide. So what you see on the top right hand side, just above that yellow bubble, is a film. I don't know, Mark, you can show the tracer on that. So the idea, the way to control the breaking of the foam is to prevent water, yeah, that's right, water draining out. So that means if the two lamellae there come close to each other, water will drain out and the foam will break. So to prevent the layers coming towards each other, what you do is add, for example, charged surfactant. The two charged surfactant layers will, when they come towards each other, they cannot come very close, only say like 100 nanometers or something. So water will not drain out, and therefore the foam will not break. And of course, using the right surfactant, you can get it to break. Okay, now you can go to the next slide again. So I just want to show also some other material there on the bottom left. Can you believe what you're looking at? That blue thing is the iron atoms. Atoms. You're looking at atoms, kid, boys, girls, women, ladies. You're looking at atoms of iron atoms on copper using modern spectroscopic technique. You can see. You also see a picture that I got from Ray Farinato on the top right, emulsion, that's milk in water or whatever. And at the very bottom, you see an insect. An insect that is heavier than water can be supported by surface tension forces. Now, if you want to learn more about it, there are two courses. I gave one along with Ray, 40 to 52, Introduction to Surface and Colloid Chemistry in the fall, and with Ray and Naga, 60 to 52, Advanced Surface and Applied Surface and Colloid Chemistry. Now, these are, if you want to succeed in any field, you have to know the surface and colloid chemistry. And it's amazing that's not a required course. If you take this course, you are one step ahead of everyone else. So I strongly suggest the 40 to 52 in the fall and 60 to 52 in spring with Ray and Naga. I used to like Ray, but not anymore because he got better evaluation than me from the students. I'm not that bad, but so anyway, I like him. I'm joking. Okay, next slide. So here is a beautiful illustration of the use of foams in the nature. Here is the mottle frog has created foam to protect its eggs from deteriorating. So it can stay like that for days or weeks until the egg is hatched. And also it can protect from viruses because of the composition of the antiviral properties of the foam. So why is that it is stable? That's because something called a hinge effect shown in the next slide. The proteins, next slide, the proteins opens up so that one side of it is the hydrophilic side is open to water, the hydrophobic side is open to air, so that the system is stable. That's why the foam is stable for as long as you want. This shows us a beautiful illustration of how you can use the structure and the dynamics of the changes in structure to control the properties of foam, froth, and so on and so forth. Next slide. So, as I said, our aim is to generate green surfactants, and microbes produce them. Microbes produce a gamut of reagents. The microbes, the red things are some microbes, and they can produce proteins in the middle and polysaccharides. And one of the biosurfactants that they produce that we use and Partha and Mark are using is the surfactant. Surfactant. that is shown on the bottom left. And that has opened up or closed depending on the pH. And the effect of that, I think, is shown in the next slide. So when you change the pH, the surfactant surface tension is changing. And you can see that when the surface tension change, the bubble size, the stability, everything will change. So this kind of surfactant, you can control the properties of the foams and everything else. Next slide. So as I said, we got this rapid grant from National Science Foundation. Rapid means we have to produce results in 6 months. We got special permission for Partha to go to the lab. And the idea is to develop robust formulations, which will last, like said, half an hour to kill the virus. And shaving cream, you don't want, shaving cream also maybe less than that. But some foams like that frog wanted it for months. You can get that by designing the formulations. And also the foams, we use the foam scan to determine the formability of a surfactant and the stability of foams. How do you monitor that? We have in the lab foam scan. You can come and look at it sometime. And you can also determine the foam size distribution. And the degree of foam deposition on different target surfaces can be determined by spectroscopically. Irina is an expert in spectroscopy, and she can do magics using spectroscopy to understand what the molecules are doing, and so on. The foam delivery options are shown here. I showed you once, but I'm showing another one at the bottom right, where you spray it on a hazmat, and it can stay there as long as you want. And you can also relate to foam composition and texture to interfacial rheology. This is what Ray is going to teach in the surface chemistry class in the spring. Now, these foams are not of use unless it can kill the virus. And we have tested the effectiveness to kill West Nile virus in Dr. Ian Lipkin's lab at Columbia. We don't have a level 4 lab. You need level 4 lab to test the Ebola and everything. So for that, you have to go to Atlanta. But level 3 labs is available. And with Dr. Ian Lipkins, you must have seen his name often in the news. He's an advisor actually to Biden in this area. So we have tested it, and this virus, these foams with the right material can kill the virus in time. Next slide. So that shows the. Go back for a second. Let me see. I'm already 30 minutes off. Okay, that shows the formability as foam generated as a function of time. That slope of that curve on the left hand is the formability, and the way it degrades after you stop the aeration is given by the slope of the curve on the right hand side. So in other words, you can determine formability and form stability. The next slide. Okay. So one very interesting thing is that the viruses and others have tethers or hairs. If you look at the extreme right, you see you have a positive hairs and negative hairs. If that's virus or microbe, it come towards glass surface. As I said, they are smarter than you all, and me too. What they will do is they will put out the complementary one, the positive one, towards the negative surface and pull in the negative one so that they will get attached. So, and this was the theory that we proposed for deposition of sweet ionic particle, and we tested that using atomic force microscopic technique. The green curve shows you get only repulsion using the anionic latex particle that we use to simulate uh, the viruses and microbes, and you see only repulsion. Above 0 is repulsion, below 0 is the attraction. So what you see is that with sweet ionic, with that negative and positive, which has the same charge, same net charge as the anionic, you get repulsion. So this supported our theory. that this is what is happening. It's published in a paper with Anand, uh, who is a professor at University of Cincinnati now. He is one of our star students, but now he's competing with me from the University of Cincinnati. But that's good. And the next slide. Now I want to show another. There are many uses of foams and froth. In addition to shaving cream, there is a very good use for uh, extracting values in space. NASA has marked one of the asteroids worth more than $10,000 quadrillion, and I need only 0.1% to do my research. There's a gold, diamond, a lot of these things. But so you can mine it using drones, robots, and then you can separate the values from the junk. The question is, how do you separate it? On the Earth, we use something called froth flotation. I think, can you show the next? But before you go to this, how do you make that work under microgravity condition? Because froth flotation works with gravity. I think next slide will show it again. No, not really. Okay. The first slide would have shown a slide of the flotation, and that works under gravity. The bubbles which collect the diamonds and all those things will go to the top, and the junk quartz will sink to the bottom. So it works very well. It has been used for 100 years or more on the Earth. But how do you make it work under microgravity conditions? Similarly, cyclones are used to separate particles and values. But we cannot use it. We have to modify the technique to use it on Mars and asteroids and so on. So that's our game. And Mark, who is one of our students, I'm going to send him. He's volunteering to go to Mars. He's listening. Anyway, actually, you're viewing his screen. So that is a challenge, and NASA is very interested in that. So we are going to try that along with other things that Mark will be doing. Next slide. So the trillions of dollars as a space in space resource, and the first trillionaire will be space miner. So I'm afraid that Mark is going to the first trillionaire. I will follow him in the second shuttle, and maybe I'll be the second one. The next slide. Next slide shows some of the recent success stories of our center, which specializes on use of surfactants. Now, how do you measure? I told you about the use of green surfactants. How do you measure the greenness? Some people, something that is green might be blue. So, Yang Shen, who is in China now, has developed a green index. And also, we have developed green molecules for frothing, for tissue engineering by Satish Ponirangam, who is a professor at the University of Calgary now. And see, what is not studied and what is most important, in my opinion, is the dynamics of these polymers and surfactants. And we have developed technique called using surface plasmon resonance, time-lapse understanding of what I call polymer surfactant dancing. That's another breakthrough. There is also Irina, who might be hopefully listening, catalysis of doped nanoparticles for changing carbon dioxide to wine, champagne. She presented a poster called Carbon Dioxide Champagne for a lot of people because you use copper oxide nanoparticles to change carbon dioxide to alcohol. And we have also a new program, not very active now, hydraulic fracturing, using surfactants along with minerals. And I told you about Ebola. And public awareness is very, very strong. By the way, we use the foams to kill the oil spill, and the success of that depended upon the emulsion droplet being stable enough so that microbes can can heat up the oil. Mark, can you show that your trace under Stephen Hawking? So Stephen Hawking have a. Oh, you can run it. Okay, go back before you do that. Has a Brave New World series, 4 of them. One of them is environment, and we Partha and I started in it. We hoped after that we'll get calls from Bollywood, Hollywood. We didn't get it, but at least we are there. And also we were covered in New York Times and Globo TV. After that Globo TV was after I was fired along with all the professors from the EPA board by the current administration. That attracted more attention. So the TV, they all came, and but the interesting thing is that I didn't say anything really bad, or what I did, they didn't, New York Times didn't print. So when they appointed 3 professors back to the EPA board, I was one of them. And also we have publications in the high impact journal, like Journal of American Society. We collaborate with a lot of universities around the world, University of Bergen in Norway, Tulane, uh, Bern, a lot of companies to collaborate with. And some of the success stories are shown on the right hand side, including applications of the food technology. By the way, food technology, without food is most important in addition to water. We need food technology in engineering school. I have been telling that to our administrators. Food tech, that's most critical. Even if you go to Mars, we are working on making bricks using Martian soils, using microbes, in collaboration with Alok Kumar, who is a professor at the Indian Institute of Science. He's the leader in that. Work was covered in the Times. There's some of the application. The Boeing, because one of the main problems in the with the planes is landing and taking off, and the landing gear goes bad. They approached us to incorporate nanoparticles, hard nanoparticles in landing gear, and we succeeded in using again polymers to coat nanoparticles on the landing gear. So these are some of the success stories. And the next slide, I think, shows. You want to show this? I don't know how much time we have. This is only less than a minute. Can you run it, Mark?
There's nothing. There's no video here to run.
There's no video.
No, not. We have videos after this, but not of Brave New World.
You don't have it there, then?
Not of this one. We have different ones.
Okay, then let's skip this one. This one, what it would have shown is the uh, is the emulsion droplet staying almost like coated by a steel frame, so that you can pull it and it won't break. It's like the silk thread. Silk thread can be like steel, and the same way, if you coat with the proteins, the emulsion droplet can stay long enough so that microbes can eat the oil. That was the idea of this uh, thing that Stephen Hawking showed, late Stephen Hawking. This slide shows the companies which used to or support uh, us or University of Florida, who is a partner with us, and yeah, some of these samples are shown there, and gold companies, personal care companies, and all that. Is that the last slide? Yeah. Okay. Yeah. Show the video. This shows. This is a nice video how the soap kills the virus. So this is a virus, and you have the tethers. You can see the proteins. And when you use surfactants, the oil into water, they form what is known as micelles. And if you want to know more about micelles, you have to take those courses. Micelles are really aggregates of soap molecules in water. You will see that in a moment. So you see the foam there. So what happens is that when you have soap molecules, it has a blue hydrophilic head and a hydrophobic tail. When it goes into water, it doesn't like water. So after the interface is saturated, it forms these nano bubbles. This is only 2 nanometers. And what would happen in the case of a virus? It will go and attach and peel off the cover of the virus, and so the virus falls apart and kills. And that is what happens in the case of use of emulsions and everything. Okay, the next slide. You don't have much time left. In the lung. Now the problem with in the corona is that you cannot breathe if you are infected with coronavirus because they eat up the lungs mini sacs that is in the lung that will be shown in a minute. And what happens is once they eat it up, you cannot breathe. And the stability of the lung of the large bubbles connected to the small bubbles or sacs is enabled by the lung surfactant. Best soap that you have is in your own lung. So what happens is that when you breathe, the stability is provided by the lung surfactant. When you breathe, the lung expands. That's it, huh? Okay, next. Then, yeah, okay. Lung expands, the interfacial area goes up, and the surfactant layer is more dilute, and surface tension goes up. Whereas when you breathe, when you exhale, the opposite happens. A condensed monolayer forms. So that is why you have that small sac stable along with the large sacs. If you didn't have the surfactant, it wouldn't be stable. Once the surfactant is destroyed or the structure is destroyed by virus, you lose that ability. The children born without surfactant, this is a disease called hyaline membrane. So nowadays they let the child inhale it, and then otherwise they will die. Is that it? I think that is it, right? Is there another slide? Oh, no, it is there's still. Oh, yeah, still another.
This is the last
20
slide.
seconds. Yeah. It's another 20 seconds. It probably shows what is happening on the surface of the molecules.
It shows what happens when you add a surfactant to the lung. Do you want me to play it?
Yeah, and you explain it. So small r, low surface tension, large r, low pressure inside the bubble, Laplace pressure. When air goes in, they expand.
Okay, that was the last slide.
Okay. So that it shows the importance of surfactant. As I said, the best soap in the whole world is in your own lung. Otherwise, you wouldn't be here today. And when that gets degraded by virus contamination or the lung structure gets damaged, you can't breathe. And that is why the surfactant phenomenon is very, very important in breathing, exhaling. So I hope you got a sample of the application of the surfaces, surfactant, and proteins and polymers we didn't cover. If you want to learn that too, you take our course, including the course of Ray Farinato. And that's it. Ray, are you there?
Yes, I'm here, son.
Yeah, there he. Oh my God, look at that caricature. Yeah, and so he'll be talking. As I said, he's a much better lecturer than all of us. So I'll stop here, and I guess, Bolun, there is some time for questions, I suppose.
Could you repeat that?
Can you control or have the students ask questions if there are questions, or faculty or anybody?
Yeah, questions. Yeah. So if you have questions, just unmute yourself and ask, or you can type it in the chat. Okay.
Unmute. I don't
Yeah.
know how. Okay.
Soma, I have a question.
Okay.
Looking at the surfactant molecule that you showed, it seems like you have the possibility of also complexing metals inside that structure. Is that known?
That is not only is known, it offers a good way to extract valuable metals such as rare earth, because you don't need much. You can, if you have a chelating agent, Nagaraj is an expert on chelating agents. If you have chelating groups attached to that, then it can chelate to only the metal that you want, not all the junk. For example, if you want only gold or lithium, you have chelating agents. Chelation is lobster. It has a lobster-like head. It can chelate just that. Yes, that is known as. Thank you for reminding me of that application.
I actually have a question. So, as a person working on economics, I was wonder how expensive is the proposed foam solution compared to the normal bleach ones, and what about the production scalability?
Yeah, that's a very good question. There are surfactants, the very cheap one to very expensive one. Like the ones that use high-end cosmetics are very expensive, like the one that is produced by Lush Cosmetics and others. Whereas the one used normally, the surfactants that are very cheap. The one that you can make from nature. When I was a kid, I remember that we used to just pluck some leaves and smash it, and surfactant is produced. Naturally, that is inexpensive. Of course, that will be mixture of surfactants. That mixing effect that you reminded me is very important. If you just use one surfactant, A, it's not probably as good as if you use two, A and B. And depending upon how you introduce A followed by B or B followed by A, it can be. So when you use mixed surfactants, the dosage required is so small that it's not expensive. So that's how you control the expense and performance by mixing the surfactants, polymers, and proteins in the right composition.
I have question about pH effect.
Yeah.
Does the role how surfactant interact with water phase and oily phase, does it impacted by a lot with pH? And also second question is it thermally and chemically stable?
Some surfactants are thermally and chemically stable. Again, it depends. For example, that surfactant, if you leave it under very alkaline conditions above pH 13, it won't be stable. But under normal conditions, they should be stable. Thermally depends on surfactants. There are some surfactants which are stable under thermally. Even the microbes, there are thermophiles. Some microbes are stable under very high conditions. There are some tube worms under the ocean. So depending on the structure and what's the wonderful, most beautiful thing is that these things can turn around, like the hinge effect I showed. They can turn around to enhance the stability. Particularly like if you touch a worm, it will make into a ball to survive. So it can change the structure. You can change the structure, and that can be controlled by incorporating the chelating groups that Naga knows about, and polymer groups that Ray talks about, and the proteins that Partha, he may be listening, that he's an expert. So by incorporating the right groups, you can make it thermally stable, high temperature or low temperature.
Okay, thank you.
Thank you.
I think one comment I want to make, this is Nag, the economics question that was asked. If you take the same system, spray versus foam, you have a significant efficiency and coverage coming from the foam because you are taking advantage of the bubble surface area, and the bubbles are now expand. I mean, you can generate an enormous surface area, and because bubbles have thin liquid films, so you are really expanding the liquid film all over, so you get the coverage is phenomenally greater compared to spray. And also Professor Soam talked about all the disadvantages of spray. It's the stability of the spray, the length it stays on a surface. It's very short. And so there are many advantages. I think this, for all else being the same, the foam would be far more effective and economic than a spray.
Yeah, that's the theme. Thank you.
I also have another question environmentally. So we use a lot of surfactant, including like detergents, right, and soap.
Yeah.
What is the environmental impact if it goes into natural water? What is the consequences?
It depends on the surfactant that you use. For example, if you wash your hands every night after for dishwashing, if you use the sodium daughter sulfate, some of the conventional one, you will be wrinkled. Like your hand will be like my face, that of my face. But if you use some of the natural surfactants, they are, and that's why we are emphasizing green surfactants. Environmentally, that is stable. So in fact, there are some pictures that I have shown in my course. The whole river in in Germany, the entire river had this big foam bridge. The foam was building up so bad. Now that's bad. But now those things are environmentally controlled to some extent. So it depends on the surfactant. Depending upon what you want to use the green surfactant, what I call green surfactant. We used to balloons shirt there. He thinks it is green. I think it is blue. So you can use the green index to determine the surfactant's greenness. Use the green surfactants environmental. It's a very important point that you raised. It is important to slowly change from the bad surfactant like SDS and others, SDS sodium dotacyl sulfate, and even then one containing benzene groups, benzene sulfonide. They are bad. Benzenes are bad for to the green surfactants, such as the surfactin. That's not surfactant, surfactin that I showed a while ago. That's a very important point.
Okay, do we have more questions? Okay, I think we are good. So yes, thanks, Tom. And this is very interesting, and thanks everyone for joining. Again, just if you are looking for videos of the recording and also our previous lectures, they should be available on our website. Okay, at the EAEE.columbia.edu. Okay.
And cookies and wines are available after the talk. They can be sent by Federal Express to those who are interested.
You're funny, so.
Okay, thanks, Tom.
Thank you, Sam.
We had a student. We had a